Bismillah ar-Rahman ar-Rahim. We have two limits. The first one is limit as n tends to infinity, the nth root of summation j from 0 to n choose j, 2 to the n minus j minus 1 to the j over j plus 1. Let's start with a conventional binomial expansion and try to manipulate it to get something like the sum here. 1 minus x to the power n is summation j from 0 to n choose j, minus 1 to the j, x to the j. Integrate both sides from 0 to 1/2. On the left-hand side, we get minus 1 minus x to the n plus 1 over n plus 1. When we use the limits of integration, we get 1 over n plus 1 minus 1/2 to the n plus 1 over n plus 1. On the right-hand side, we have the integral x from 0 to 1/2 of x to the j. This is x to the j plus 1 over j plus 1, like here. When we use our limits of integration, 0 gives 0. When we use 1/2, we get 2 to the minus j minus 1 over j plus 1. We are very close to what we have in the limit statement. If we multiply both sides by 2 to the power n plus 1, we get 2 to the n minus j. On the left-hand side, we get 2 to the n plus 1 minus 1 all over n plus 1. This is exactly what we have here. Raise both sides to the power 1 over n, then take the limit as n tends to infinity. Our desired limit is limit as n tends to infinity of 2 to the n plus 1 minus 1 to the power 1 over n times 1 over n plus 1 to the power 1 over n. We can obtain both limits using L'Hopital's rule. Let's obtain the limits of the logarithms and then we exponentiate. Limit as x tends to infinity, log 2 to the x plus 1 minus 1 over x is the limit as x tends to infinity. The derivative of the denominator is 1. The derivative of the numerator is 1 over 2 to the x plus 1 minus 1. Then we have 2 to the x plus 1 times the natural logarithm of 2. As x tends to infinity, this ratio tends to 1. We are left with log 2. E to the log 2 is equal to 2. For the other quantity, let's consider limit as x tends to infinity, log x plus 1 over x. Applying L'Hopital's rule, the derivative of the numerator is 1 over x plus 1. The derivative of the denominator is 1. As x tends to infinity, 1 over x plus 1 tends to 0. E to the power 0 is equal to 1. The desired limit is equal to 2. The second limit is limit as x tends to 1 from below of this infinite series, n from 1 to infinity, minus 1 to the n minus 1, x to the n over 1 plus x to the n. X is strictly less than 1. Let's call this sum omega of x. We can split this sum into odd and even terms because we have here minus 1 to the n minus 1. If n is replaced by 2n minus 1, which is odd, we get plus 1 times x to the 2n minus 1 over 1 plus x to the 2n minus 1. If n is replaced by 2n, we have x to the 2n over 1 plus x to the 2n, and this becomes minus 1. Combining the two terms, we have 1 plus x to the 2n times 1 plus x to the 2n minus 1. In the numerator, we have this times that. This is x to the 2n minus 1 plus x to the 2n, x to the 2n minus 1, minus this times this denominator. We have x to the 2n minus x to the 2n, x to the 2n minus 1. These terms go away, and we are left with x to the 2n minus 1 minus x to the 2n in the numerator. Multiply and divide by 1 plus x. Here is 1 plus x in the denominator. When we multiply these two terms by 1 plus x, we get x to the 2n minus 1 minus x to the 2n plus x to the 2n minus x to the 2n plus 1. These two terms go away. In the numerator, we are left with x to the 2n minus 1 minus x to the 2n plus 1. We need a lower and upper bound on omega of x. To upper bound omega of x, we need to increase this quantity by decreasing the denominator. Note that x is strictly less than 1. We reduce the value of the denominator by increasing the power. So to upper bound, we keep this 1 plus x to the power 2n. We raise this power from 2n minus 1 to 2n. Because x is smaller than 1, x to the 2n is less than x to the 2n minus 1. We get an upper bound on omega of x. Moreover, we multiply the numerator and denominator by x. Here is x downstairs. When x is multiplied by this bracket, we get x to the 2n minus x to the 2n plus 2. This is the upper bound on omega of x. We also need a lower bound, and for the lower bound, we will replace this 2n by 2n minus 1, so that we get 1 plus x to the 2n minus 1 all squared in the denominator. We also multiply and divide by x squared. we keep x squared in the numerator, and we divide this bracket by x squared. Now we have x to the 2n minus 3 minus x to the 2n minus 1. This is a lower bound on omega of x. Hopefully, when we take the limit as x tends to 1 from below, the upper and lower bounds converge to the same limit, and this will be the solution to our problem. Suppose that t is between x to the 2n plus 2 and x to the 2n. Add 1 to all sides. Take the reciprocal, so the inequalities will be reversed. We will get that 1 over 1 plus x to the 2n is less than or equal to 1 over 1 plus t, which is less than or equal to 1 over 1 plus x to the power 2n plus 2. Square all sides. Now we integrate all sides from x to the 2n plus 2 to x to the 2n. Let's focus on this part here. We have integral t from x to the 2n plus 2 to x to the 2n, 1 over 1 plus t all squared. This side is not a function of t. When we integrate, we get this same quantity multiplied by the difference between the upper and lower limits of integration, x to the 2n minus x to the 2n plus 2. Sum both sides, n from 1 to infinity. When we do this summation, we will get this quantity here, which is part of the upper bound on omega of x. Let's sum the integrals. When n is equal to 1, we are integrating from x to the power 4 to x squared. When n is equal to 2, we are integrating from x to the power 6 to x to the power 4. When n is equal to 3, we are integrating from x to the power 8 to x to the power 6, and so on. The lower limit of integration gets closer and closer to 0 as n increases, because x is strictly less than 1. When we sum this side, n from 1 to infinity, the integral becomes from 0 to x squared. We are integrating 1 plus t to the minus 2. The antiderivative is minus 1 plus t to the minus 1. When we use the limits of integration, we get 1 minus 1 plus x squared to the minus 1. This is x squared over 1 plus x squared. The upper bound on omega of x is this quantity divided by x times 1 plus x. The upper bound is x divided by 1 plus x times 1 plus x squared. Now consider t between x to the 2n minus 1 and x to the 2n minus 3. Add 1 to all sides. Take the reciprocal and square to get this inequality. This time we will focus on this part. We integrate both sides from x to the 2n minus 1 to x to the 2n minus 3. Because there is no t here, when we integrate, we get x to the 2n minus 3 minus x to the 2n minus 1 divided by 1 plus x to the 2n minus 1 all squared. Sum from 1 to infinity. When we sum this side, we get part of the lower bound on omega of x. Let's see what is going on to the integral. When n is equal to 1, we are integrating from x to the minus 1. When n is equal to 2, we are integrating from x cubed to x. When n is equal to 3, we are integrating from x to the power 5 to x cubed. When n is equal to 4, we are integrating from x to the power 7 to x to the power 5, and so on. When we sum, the overall effect is that we are integrating from 0 to 1 over x. We get 1 over 1 plus x. This is multiplied by x squared over 1 plus x to get a lower bound on omega of x. Omega of x is lower bounded by x over 1 plus x all squared and is upper bounded by x over 1 plus x squared. As x approaches 1 from below, this approaches 1/2. When we square, we get 1/4. Here we get 1 over 2 times 2, which is also 1/4. The limit of the sum n from 1 to infinity, minus 1 to the n minus 1, x to the n over 1 plus x to the n, as x approaches 1 from below, is 1/4.